All right, lesson 5, we're talking about entropy. Entropy is disorder. And so if I look at this example here, I have, in this case, all of these dots. I have 9 dots. These can represent particles or gas or whatever. And then I have 9 here. If I look at it, this has higher disorder than this. This is more organized. So this is organized. So this is disorganized relative to the other. So when we talk about entropy, this will have high S, this will be low S. So high S, low S. So if I go from here to here, my delta S is going to be low S minus high S, because it's always final minus initial. And so low S, so let's say this is 5, this is 10. I don't know exactly what they are, but this is bigger. So this is going to give me a negative delta S. A negative delta S we can also write as less than 0. Okay? Whether we write it as negative or less than 0, what that means is becoming less disordered. Or another way to put this, it's becoming, less disordered. Hence, delta S is going down. Or another way is it's becoming more organized. Right? It's going to get more order. I'm going from disorder to order. Okay, let's do some problems. We started these in the lecture. Right? So in the first one, A, we said H2O liquid going to solid. That's water freezing. When we go from liquid to solid, what are we doing? We're going from something that's disorganized to organized, so it's getting more organized. So again, delta S is less than 0. If I'm going instead the opposite way from solid to liquid, my delta S is going to be positive. Okay? So that is NH3 solid going to NH3 liquid. We said that this is delta S is positive. Okay? Let's do C. In C, we're going from NH3 liquid to NH3 solid. Okay? We can go through and we could try to figure this out, or we can just say this is the opposite of B. And so if this is positive, this must be negative. Okay? Less than 0. All right, D, we have water at 80 degrees going to form room temperature. Room temperature is about 25 degrees C. Okay? So this is water. So what's happening? Water at 80 degrees is going to be more disorganized. So it'll have a high S, whereas this will be low S. Okay? So I'm going from high S to low S. So I'm going from low minus high. So this is going to be less than 0 or negative. Let's do E. In E, we're going from Na plus and Cl minus to NaCl. This is solid. These ions, these are aqueous. So we're going from aqueous to solid. Now let's remember what aqueous means. Aqueous means ions inside water. So this is going to be really disorganized, right? Think of salt water. Whereas NaCl solid, this would be a salt crystal. Okay? So this is more organized, so it'll have a lower S. So I'm going from high to low, so my delta S will be this minus this. So again, it'll be negative or less than 0. All right, let's go through these on the screen. So on the screen, we said that C was the opposite of B, so delta S was negative. And then, sorry, 1 second. Delta S is negative in this case. If I decrease temperature, I'll also get a negative at delta S. And if I go from mixture to pure, I'm getting more organized, so my delta S will be less than 0. Okay, so let's move on, and let's do one more problem. Now we're going to try to calculate delta S. This last problem was predicting delta S. Now we're going to actually calculate delta S. All right, so in 3b, we're taking H2O, or sorry, in problem 3b, we're going from H2O liquid to H2O gas. And so what we can do is we can look up in the back of the book the delta S's, the standard S's, the standard entropies. And I can see there I have 69.9 for H2O liquid. And I have 188.7 for joules per mole K. That's for the gas. So my delta S is just going to be my products minus my reactants. And that's going to get me positive 118.8 joules per mole K. It makes sense, or actually, sorry, the moles goes away because in this case, I'm multiplying by 1 mole, and so that goes away. So I have 118.8 joules per K. That makes sense because entropy is increasing. I'm getting more disorganized. Okay? All right, let's go on to our last problem. This is 2H2 gas plus O2 gas goes to form 2H2O liquid. All right, so I have this equation, or I have this reaction. I'm told this is 130.6. Okay. O2 is 205. Let's make sure we get the right H2O. It's liquid, so it's 69.9. And all these are in joules per mole K. So I'm going to go ahead and I'm going to calculate my delta S. It's going to be products minus reactants. Remember, I need to use that coefficient in front, right? That coefficient has to be there. I did it in the last one because the coefficients were 1 and 1. So multiplying by 1 doesn't matter. And then I'm going to subtract off 2 times 130.6 and then add in this 205. This is my reactants. Right? Notice I don't include anything up here because it's 1. All right? So when I do this, I go ahead and I put these in the calculator. 2 times 69.9 is going to give me 139.8 minus 466.2, and that's going to get me 326.4. It'll be negative joules per K, right? These are in joules per mole K, but because these are in moles, that cancels out the moles. All right, so this is my answer. And it makes sense because look at what's happening. We're going from gas to liquid. So we're becoming more organized or more order, right? So that means it'll become less disordered. So that means why it's negative. Here are these problems once more on the screen, right? We go ahead and we always do products minus reactants, taking into account any coefficients. You can see here, I actually use the 1 and the 1 because those are the coefficients in the problem. All right, that's it. Talk to you later. Bye.